Welcome to The Explainer. Today we're going to tackle a physics mystery that completely shattered a centuries-old understanding of what light is, and in the process, it basically launched the entire quantum revolution.
For centuries, physicists thought they had it all figured out. Light was a wave. End of story. But then, this one bizarre experiment came along that just didn't make any sense. We're going to treat it like a scientific crime scene, because the clues were pointing in a completely new and frankly, super weird direction. All right, so in any good mystery, you've got to set the scene, right? So let's establish what everyone thought was true before all this strange new evidence turned up. So back in the 19th century, everybody was on the same page. Light is a wave. Simple. Think about it like a wave in the ocean. A bigger, brighter wave should carry more energy, right? It should make a bigger splash. But then came this thing called the photoelectric effect, an experiment where light knocks electrons off a metal surface, and it just completely broke all the rules. So the setup for this experiment, it was actually super simple. You just take a special metal plate, you stick it in a vacuum tube, you shine a light on it, and pop, electrons get blasted right off of it. This creates an electric current that you can measure. A really simple setup that, well, it produced some truly baffling results. And right away, here's the first major clue that something was seriously off. It turned out the brightness of the light wasn't the important part. It was the color, or to be more precise, its frequency. A really faint violet light could knock electrons free, but an incredibly intense, super bright red light did absolutely nothing. And that made no sense at all.
I mean, this just flew in the face of everything they knew. The wave theory was crystal clear. A really powerful blast of red light, like a giant ocean wave crashing on the shore, should have had more than enough oomph to knock those electrons loose. But it just didn't. It was a total contradiction.
Okay, so that was clue number one. Clue number two was just as baffling. The speed. The very instant the light hit the metal, the electrons were gone. There was zero time lag, none. You see, if light really was this gentle, continuous wave just washing over the surface, you'd expect an electron to have to kind of, soak up energy for a bit before it could escape. But that's not what happened at all. The effect was immediate, as if the electron got hit by a single, concentrated projectile. So, at this point, classical physics basically hit a brick wall. The clues didn't add up. The case had gone cold. Until, that is, a radical new idea from a totally different area of physics came along and provided a crucial lead. And then, the first big break came from a place nobody expected. A physicist named Max Planck was studying something that seemed totally unrelated, heat radiation, and he made this wild suggestion. What if energy isn't a smooth, continuous flow? What if it comes in tiny, individual packets? He called them quanta, and this idea was the key our mystery needed. And this is where our story's detective, a young Albert Einstein, enters the scene. He saw what Planck was talking about, and he immediately saw the connection. He took this radical idea of energy packets and applied it directly to the photoelectric mystery. Einstein had this radical, game-changing thought. He basically asked, okay, hold on, what if we've been looking at this all wrong? What if light isn't a wave at all, but a stream of these tiny energy bullets? What if each one of these bullets delivers all of its energy in a single concentrated punch? And he gave these little packets of light a name: photons. A photon is a single massless particle of light energy. This one simple idea was about to change physics forever. And the core idea, the real key to the whole thing, is boiled down into this one beautiful equation. It says that a photon's energy, its punch, depends only on its frequency, which is basically its color. Not its brightness, not its intensity, just its frequency. And this was the key that would unlock the whole thing. So, armed with this brand new photon theory, Einstein went back to the crime scene and suddenly, everything just snapped into place. Every single baffling clue finally made perfect sense. And this is where you can just see how brilliantly it all works. That question about why color matters? Solved. A high-frequency violet photon has enough energy for the job, while a low-frequency red one just doesn't. The mystery of why it's instant? Solved. It's a direct one-to-one collision between one photon and one electron. And what about brightness? Well, that's just more photons hitting the target, not stronger ones. Okay, let's use an analogy to really nail this down. Imagine an electron trapped in that metal plate is like a student who needs to get past an electric fence to grab an exam paper. That fence represents the minimum energy the electron needs to escape.
A low-frequency photon, or red light, is like a student who just can't jump that high. They don't have enough energy. You can send a whole army of them, one after another, but not a single one is getting over that fence. But a high-frequency photon, or violet light, that's your star athlete. It has all the energy it needs to clear the fence in one single effortless leap. So, case closed, right? Well, yes, but the verdict, the conclusion, it uncovered this whole new reality about our universe that was just mind-blowing, stranger and way more profound than anyone could have possibly imagined. What this all proved is that light is living a double life. It's just bizarre. Sometimes it acts exactly like a smooth, continuous wave, and other times, like in this experiment, it acts like a stream of individual particles. It's both at the same time. And don't underestimate how huge this was. This idea is literally the foundation of all of quantum mechanics. It's the reason we finally understood how light and matter interact. It's also the reason we have solar panels, automatic doors, and yes, the digital camera inside your phone. All of it comes back to this discovery. And if you need any more proof of how massive this was, get this. In 1921, Albert Einstein won the Nobel Prize in physics, but, and this surprises a lot of people, it wasn't for his world-famous theory of relativity. Nope, it was for this, for cracking the case of the photoelectric effect and discovering the law that explains it. So we're left with this really weird, but absolutely true, conclusion about reality. As the physicist Louis de Broglie put it, we just have to use whichever theory fits the experiment. Is light a particle? Is it a wave? The answer is yes. It just depends on how you're looking at it. Okay, so this is the final mind-bending thought I want to leave you with. This whole mystery proved that something we thought was a wave, light, can act like a particle. Well, that discovery blew the doors wide open for scientists to ask the opposite question. If waves can be particles, can particles, like the very electrons that make you up, act like waves? And the answer, incredibly, is a definite yes. But that is a whole other mystery for another explainer.